Hello, it's time for a new topic, and that's going to be extended bodies. So everything that we've done so far in classical mechanics has just been looking at points moving around in space. So we started off with kinematics of just describing how those points move. Then we went to dynamics and how the forces are affecting that motion. But those points, they can't rotate or spin or anything like that because they don't have any volume. There's no extent to them. So when we start looking at extended bodies here, we're wanting to be able to describe how bodies might be rotating while they're moving around. So this is just a different way of describing the motion of objects. We're still looking at forces and at matter, at kinetic energy. These are all the same things. We haven't got new stuff turning up. It's just a new way of describing things that may be rotating. So let's deal with some terminology first of all, and that means moments, couples, and torques. So moments is by far and away the most important one out of all of these. Let's think of a simple extended object. So let's go for a rod. So we just got a straight line. We do a lot of work with rods when we start off looking at moments because it's one of our simplest extended objects. It's just a straight line of we'll say it's a uniform rod, so it's got a mass of m distributed over a length of l, and the mass is distributed evenly. So if you take any chunk of a particular size from this rod, you'll get the same amount of mass. It's just an even distribution of mass along the length. So if we've got this this rod here now, up until now we've just been thinking about points where we might say let's consider this rod, say, to be, because it's uniform, just a point at the center of the rod, and then we can push this thing around. So if we were going to just translate this rod, we could translate it upwards by moving the whole thing just straight up, so it's at the same horizontal orientation, and we've just applied a force which has moved it straight up, and it's moved it somewhere else. Well, that's great. We can keep doing that. All of the points along the rod, if we're going to think of this rod as being lots of little masses stuck together, they've all moved by the same amount. They've all been affected by the same force. If we're looking at the energy of it, the kinetic energy of the rod, if it keeps on moving, will be evenly distributed along the rod because all bits of the rod are moving exactly the same way. Now, that all starts falling apart if it starts rotating. If we pushed at one end, then this end will start moving more than the other end. It's going to start rotating around. So that might move up. Okay, the whole rod might start moving upwards, but by the time the center of the rod has got to here, it might now be at an angle. So different parts of the rod will have more energy than others because these bits at one end are moving faster than the bits at the other end. So this makes it very difficult to describe what's going on with the skills that we've already got, just using our Newton's laws and translational movement. So we need to start bringing in a way of describing this rotational part of everything that's happening. And we're doing this, first of all, right, let's start with a moment. Let's put a definition of a moment in, and that'll help us unpick everything that's going on. So we've got a force. And these are just the same forces that we've been thinking of up until now. But we've got some force, and we're going to multiply by a perpendicular distance of that force from a point or axis of rotation. Point or axis of rotation. And it's the multiplication of these two things, the force times the distance, that gives us the moment. But we're also going to want to specify in this as well, we're going to need to specify the direction that this is acting in, because we could be making something rotate clockwise or anti-clockwise, so we need to specify that all in it as well. Right, let's go back to this rod then and see what's going on. So I'll draw out another rod. We need this point or axis of rotation because there's 3 bits in here that we've got for defining the moment along with the direction. So 4 bits. We've got the force, the perpendicular distance, the point or axis of rotation, and the direction. Okay, so let's say we've got our point or axis of rotation is at one end of the rod. Say that's the thing that is being rotated around. So let's say that's a fixed point at the moment. We've stuck this rod on something, we've hinged it to something, and it's just going to be moving around in a circle around this point that's fixed at one end. So we don't have to think about any kind of translation. We've only got rotation going on here. So that's good. Now we can apply a force to it. So I'll start off by saying we've got some force at the other end, F, which is perpendicular to the rod. We know the rod is of length L. So we've got loads of stuff going on here already. We've got our force, so that bit's done. We've got our perpendicular distance of the force from the axis of rotation, because that's L, so that's done. We've got our point or axis of rotation, and then we've got the direction, which is going clockwise. So we can now say for this that our moment is equal to F times L, and it's going clockwise. So this is good. What if we had done a different force, which was going off at an angle? So say that's still M, and it's going at an angle theta, and we're now at some distance x. Okay, well, F is fine. We've still got the force. We've got the same point axis of rotation. We've got the same direction. It's still going to make this thing rotate clockwise. The difficulty now is the perpendicular distance of the force from our axis of rotation. So we can get this in two different ways. You can either take the component of the force, which is perpendicular, or we extend the line of the force and find its closest approach, because that would be the perpendicular distance. Now, both of these are exactly the same thing, because we're either going to get a sine theta in order to get this side of the triangle here, or we're going to do a sine theta in order to get the component of F. So we're going to end up in the blue case with a moment that is equal to F times X this time, because we're not at the other end of the rod, we're this distance X away, and then a sine theta, and then again that's clockwise. So it's quite easy working out these moments. Now, in this case, because this point or axis of rotation is fixed, we can describe all of this, and this will come up in later videos. We're not going to get all of our description techniques into this video, but we would be able to describe everything that's going on in terms of rotation. So when it comes to rotation, we're talking about, what is the moment? So we're moving from forces to moments, because forces just on their own, we're looking at the linear transformations, translation through space, not the rotation. So we're going from force to moment, and we'll be looking at a new way of, rather than having our linear kinetic energy, we're going to go to angular kinetic energy. It's still kinetic energy. There's no sort of difference. It's just an easier way of describing it in this. And similarly, we're going to go for our momentum, we're going to go from linear momentum to angular momentum. Again, it is exactly the same thing. It's just a different way of describing it. It's still momentum. It's still how much motion have we got. It's still the mass times the velocity. But we want to handle these things differently, because as soon as this rod starts moving round clockwise, think of what's going on inside the rod. If you take a little chunk of the rod at one end, so that as far away from the axis of rotation as possible, this is going to be moving faster than a bit of the rod which is closer to the axis of rotation. So this bit up here has got more kinetic energy, it's got more momentum compared to this little bit closer to the axis of rotation. So we want an easy way of being able to describe all of this, because trying to do that by looking at the linear motion of all of the bits along the rod is going to be a nightmare. So we're going to be developing a description that means we can do this all in an angular fashion, and I'll be putting that into the next video. So that's what's going on with moments. Oh, I suppose I should mention as well, so we've talked about this with this fixed point of rotation here where everything's going around. You can get a mix of the two. So say all of this was moving while it was also rotating. So you've got all of this rotation round the fixed point here, but say we were in a different frame of reference where that fixed point was now moving through space. So we've got rotation around that point still, but that point is itself moving, in which case you've then got a combination of linear and angular motion. So you can put these two things in together. I suppose you get this if you were going to think of the orbit, say, of the Earth around the sun. We could describe that as the sun we could think of as a fixed point or nearly a fixed point, but it approximates nicely to a fixed point, and say that the Earth is nearly going in a circle. So the Earth is orbiting around and around on this. So we could describe it in this case purely in terms of rotational movement. But of course, the sun is actually moving. So you could set the sun off in motion as well. We can still describe the Earth's motion around the sun purely rotationally, but then we've got another element of motion that you then have to put on top of it. So you can combine these descriptions of motion together. But at least initially, we'll just be looking at things that are just rotating. They're not going to be rotating and translating at the same time. So that's moments. And it brings us to a new way of getting equilibrium. So up until now, when we've looked at equilibrium, we've had some point in space. We've had various forces applied to that object, and then we've resolved the forces in two perpendicular directions. And we said, well, if there's no net force in either direction, then that object is in equilibrium. It's not moving anywhere, because we know from Newton's second law that if something's going to be equilibrium, well, I say it's not moving anywhere, it's not accelerating. So you can have it as not moving in a particular frame of reference, because we know from Newton's laws if there's no net force, then there's no acceleration. So the object is in equilibrium. It's either not moving or it's just moving at a constant velocity. We've now got a new thing that we need to add into equilibrium now. But of course, you could have a fixed point, but it could be moving around. It could be rotating. So we now need a rotational equilibrium as well. And rotational equilibrium is then saying that the clockwise moments are equal to the anti-clockwise moments. So that's what we need for rotational equilibrium, and this will be rotational equilibrium about a particular point. So we'd pick some, if we had this rod again, and you want to say, okay, it's not rotating at all, it's just stuck where it is, we can pick any point along this rod because none of them are moving, and we can say, okay, we'll pick this point here. We might have various forces which are being applied to this rod in different directions at different points along the rod. We can say, okay, from here, let's get the moment of each one of these forces, and the clockwise ones must be equal to the anti-clockwise ones, because if they weren't equal, the thing would be moving. We'd have a resultant turning force. So we'll be using this a lot as well, because we'll be looking at extended objects that are in equilibrium first of all, before thinking about what's going to happen when they're moving. So it's going to be, okay, how do we keep this rod fixed? So we'll be looking at rotational equilibrium as well as all of the equilibrium that we've looked at already, our translational equilibrium. Right, so that's dealt with moments. Now, couples and torques, these are a lot quicker to go through. A couple is just a pure rotation. So you can apply a force to an extended object that might both rotate it and translate it. That's quite conceivable. I mean, you know what it's like. You put a pen on the table, you pick the pen up from one end, then it's going to move the pen up in the air, and if you're not holding it too tightly, the pen will rotate from being horizontal to vertical. So you've done both things. You've picked it up from when it was flat, you've lifted it up in the air, you're now holding it vertically, it's rotated and it's lifted. So that's applying a force which is doing both things. Now in a couple, you don't get the translation. And the way that works is it's always going to be equal and opposite forces that aren't going through the same line. Some force going upwards here, the same magnitude force in the opposite direction over the other side. Now, whatever I do with these, I mean, this isn't going to create any translation, because if we resolve vertically, they're equal and opposite and they're going to cancel out. But they are creating a moment, a net moment on this that are going to make the rod rotate, because it doesn't matter which point wherever I pick a point or axis of rotation, if I pick a point here at this end of the rod, okay, this F here is going to dominate because it's a greater moment because it's further away from the point of rotation, so it will start moving clockwise. If you take a point in the middle, well, both of them are going to be spinning it clockwise. They're both acting in the same direction. Pick a point in the at the other end of the rod. Now this F is dominating. So yeah, whatever you do, these wherever you pick your point of rotation, we're going to get a clockwise moment, a clockwise moment, a clockwise effect, turning effect, because of this. So a couple is just a pure moment. You don't get any translation because they have to be equal and opposite. Of course, they don't have to be applied perpendicular to the rods. They could be equal and opposite at the same angle, the same slanted angle to the rod, but providing they're not going through the same point, because if they were going through the same point, you wouldn't get the rotation. They just cancel each other out, so they can't go through the same point. And providing they are directly opposite in direction, because then it gets rid of any translation, then we've got ourselves a couple. So that's all we're talking about with a couple. It's just a special setup on moments. And then a torque. So a torque is a moment of a couple. So if we've got a couple, how do we how do we specify the magnitude? How great, how strong a couple is this? And that's what the torque is. So yeah, our torque is just, so it's the moment of the couple. And interestingly, with that, is it doesn't matter where you put your axis of rotation on this. So let's go back to, we've got a rod, we've got let's put the couple acting on opposite ends. So we will pick our axis of rotation. So say you picked one end here and that's of length L. Well, our total moment that we've got here about that point is FL. If you pick the bit in the middle, say as a point, then we've got FL over 2 plus FL over 2, which again is FL. Say you pick some point, I don't know, all the way over here, which is 5L away from one end of the rod, then we've got 5LF going anti-clockwise and we've got 6LF going clockwise. So the difference again is FL. So it doesn't matter where you put the point or axis of rotation for a couple, you're always going to get the same torque. It always produces the same moment. So this is a good way then of comparing what is the strength of a particular couple. So you might see this in machinery and engines and things like that. It's useful in engineering because then you can just directly compare how much rotational effect is coming out of a particular machine by saying, well, what's the torque of the machine? It doesn't matter about the specifics of where you put the axis of rotation. You're just saying how much turning effect is being produced. So that's what's going on with a torque. So yeah, couples and torques are much easier to explain than moments. They're much easier to deal with, and this is why we spend most of our time looking at moments, because they're applicable in so many situations. You've got more moments than you have couples and torques. So now we've got all of this together, we need to start putting together how we're going to make this transition from all of our linear stuff into our angular stuff. We've already done the step of force into moment, but now we're going to have to take steps from kinetic energy into our rotational kinetic energy and linear momentum into angular momentum, and I'll put all that into the next video. because as we've seen when we were discussing this rod rotating, all of these things are now going to depend upon the distribution of mass around the axis of rotation. So we need to have some way of taking that into account, because mass which is further away from the axis of rotation has got more energy and more momentum than the stuff that's close to the axis of rotation. So we need to have all that built into our descriptions. So that's going to be the really new stuff in all of this, and I'll put that in the next video.